today's concept is total probability. Total probability theorem. The statement of total probability theorem is the probability probability P of A of any event in in sample space yes can be expressed can be expressed in terms of in terms of conditional probabilities. So this is the statement in terms of words. This is the statement in terms of words. So suppose suppose it can also be represented like this. Suppose if we given n mutually exclusive events, n mutually mutually exclusive events, that is Bn, where where n equal to 1, 2, 3, and so on and so on. And we say here the events are mutually exclusive. That means the intersection between, that means Bi intersection Bk is equal to 5. That means these events are mutually exclusive, means there is no common point between them. So these events can be represented like this. Suppose if you take the Venn diagram, like this, and if you assume this is B1, this is B1, and if we assume this is B2, this is B3, B4, B5, B6, and so on. You can assume number of events. So B1, B2, B3, B4, B5, like that. And if you see, there is no common event. There is no common event between 1 and 2. There is no common event between 1 and 2. Similarly, there is no common event between, there is no common space, or you can call space also, common space between 2 and 3 also. So likewise, there is no common event between everything here, if you see here. So that's why these events B and B1, B2, B3, and so on, all are called what? Mutually exclusive events. And from the Venn diagram, we can also say that the sum of all the events, that is the sum, sigma bi is equal to, yes, sigma bi is equal to, yes, that is if you add all the things, that is if you add b1, b2 space, b3 space, b4 space, b5, b6, b7, everyone, if you add all the things, that it gives you the S means here it is sample space. Sample space. This is how you have to remember. So if you add all the things, you get sample space, and you have to find out what here probability of an event A. So the event A can be represented like this. Suppose you are assuming your event is like this. Your event is like this. This is an event A. If you assume A as like this, and see how it will be written. No. Now, according to total probability, the theorem states the statement of the theorem in terms of mathematical relationship. In terms of mathematical relationship is like this. This sigma I equal to 1 to n p of a given bn into p of bn. This is the mathematical statement of your total probability. Of our total probability. So we have to prove this one. We have to prove this one. So now, proof. Proof. Suppose we write. Shall I write? I will write A is equal to A intersection. Yes. I will write A equal to A intersection S. So where S is the sample space, A is my event. So if you write A equal to A intersection S, So there is nothing but it is equal to A. And we already know that A intersection S can be written as the summation of Bn. We already know that one. Summation of Bn. Since all the events are mutually exclusive events, you can take out this summation into right side, left side, and you can write like this: A intersection Bn. So, since all the events are mutually exclusive events, the above equation can be written like this. The above equation can be written like this. So, A equal to like this. And if you apply probability on both sides, if you apply probability on both sides, it can be written as P of A equal to summation of I equal to 1 to n A intersection Bn. A intersection Bn. Since the summation is here summation is from 1 to n. Here also the summation is from 1 to n. Summation is from 1 to n. And end section be how end section be written. The summation point is written on the left side, and if you move the A to the right side, it will be written like this. It is A intersection B n. So A intersection B. So we know that the conditional probability, how a conditional probability written as A given B is equal to, we already know that A given B equal to P of A intersection B divided by P of B. P of B. So we know that P of A given B equal to P of A intersection B divided by P of A. And if you want P of A intersection B, P of A intersection B, it can be written like this: P of A given B into P of B. P of A given B into P of B. But here what we want: P of A intersection Bn. In the above function, we have already what? We have this one. This one. What is this one? A intersection Bn. P of A intersection Bn. So P of A intersection B, how it will be written from the above formula? It can be written as P of A given Bn into P of Bn. So wherever you are having Bn, I am B. Wherever you are having B, I am replacing this B with what? Bn. Then it becomes what? P of A given Bn into P of Bn. I am assuming this one as equation 2, and I am assuming this one as equation 1. Sorry, not this one. This. I am assuming this one as equation 1. So, and I will substitute my 2 in equation 1. Equation 1. Then it becomes what? P of A is equal to sigma I equal to 1 to n, and you have to replace this P of A intersection B with this one. You have to replace P of A intersection Bn with this one. Then it becomes P of A given Bn into P of Bn. So this is the statement of total probability, and we have proved this one. And moving again, I am explaining one more time. So what I am taking here, I took n mutual exclusive events. I took n mutual exclusive events, that is B1, B2, B3, and so on Bn. So their intersection is always is equal to 5. Why? Because they are mutual exclusive events, so there is no common events between them. So that's why it is a null set. A null set. So they can be written like this. And we took an event A inside this sample space, and we have to find that the event A probability in terms of B1, B2, B3 conditional probabilities. No. For that purpose, we have one proof. The summation of all the events mutually exclusive here is equal to S. Is equal to S means sample space. And the statement of your total probability is like this: P of A equal to sigma I equal to 1 to n, P of A given Bn into P of Bn. So this is the statement I have to do, and from that we have to take like this proof. So we know that the A, an event A can be written like this: event A is equal to A intersection S. A intersection S, where S is the sample space. So from the top we know that S can be written as summation of Bi. So summation of Bi, or whatever maybe, it can be also written as like this. It can also be written as Bn. So summation of I equal to 1 to n Bn. So since the events are mutually exclusive, You can write like this. You can take the summation to the left side and move a to the right side. It becomes what? Sigma I equal to 1 to n a intersection bn. So afterwards, I have applied in this step. I have applied what? I have applied probability on both sides. Probability on both sides. On both sides. On both sides. Then it becomes what? P of A equal to sigma equal to 1 to n P of A intersection Bn. A intersection Bn. But we know that from the conditional probability statement, P of A given B equal to P of A intersection B divided by P of B. This is the formula I have now. So, but here what I have to know? P of A intersection Bn. So, wherever you are having B, you should replace with what? Bn. Then it becomes like this. It becomes like P of A given Bn equal P of A given Bn into P of Bn. I am assuming this equation as 2 and I am assuming this equation as 1 is the equation as 1 and I have substituted 2 in equation 1. Substitute 2 in equation 1. So substitute equation 2 in where? In equation 1. Then I will get like this and I will get like this. So hence total probability theorem is true. Hence total probability probability theorem is why? Because we have achieved our statement, that statement in the above function. So the next one is Bayes theorem. So Bayes theorem is nothing but the extension of it is the extension of total probability. So we already know that the total probability P of A equal to P of A given Bn into P of Bn. This is just now only we have derived. So in the same way, it is the extension of Bayes theorem is the extension of your total probability. So the total probability, using the total probability, if you what is meant by your Bayes theorem says is Bayes theorem says the total probability can be extended. The total probability theorem can be extended to any events, can be extended to any two events, extended to any two events. Here I assume that two events are A and B n. B and what the from the base, then what we have to find out is P of Bn intersection P of Bn intersection A. So we already know that from the condition probability, P of Bn intersection A can be written as P of A intersection B divided by, sorry, can be written as it can be written as P of Bn intersection A divided by P of A where the condition is P of A not equal to 0 as it is in the denominator. In the same way, we can also know that P of A given Bn is equal to P of A intersection B given P of Bn. P of Bn. So from this we can write P of A intersection Bn as P of A intersection B is equal to P of A given Bn into P of B, A given Bn into P of Bn. So let us assume this as equation 1. Let's assume this as equation 1. Equation 1 and this as equation 2. This as equation 2. Okay, and substitute equation 2 in equation 1. Equation 2 in equation. So substitute equation 2 in equation 1. Equation 2 in equation 1. What we will get is P of Bn given A is equal to P of A given Bn into P of Bn divided by P of A. P of A. This is we have obtained. Let us assume this is equation number. But we already know that from from the total probability from the total probability P of A, that P of A can be written as summation sigma I equal to 1 to n P of A given Bn into P of Bn. This is already we know. This is from total probability. And if you substitute this equation in the, let us assume this equation 4. If you substitute equation 4 in equation 3, you will get P of Bn given A is equal to P of A given Bn into P of Bn divided by summation of sigma I equal to 1 to n P of A given Bn into P of Bn. So this entire thing is called nothing but the proof. It is called as Bayes theorem proof. Bayes theorem proof. So what is the basically Bayes theorem indicates? We have to find out. We have to find out basically P of Bn given A using total probability is nothing but Bayes theorem. So I am explaining one more time, going under the back. So what is the Bayes theorem states? The total probability theorem can be extended to any two events. The two events I am assuming here is A and Bn. A and Bn. So from this is the proof. Proof starts from here. Proof. So we know that P of Bn can given A as written as P of Bn intersection A divided by P of A, and I am assuming this as equation number 1. Equation number 1. And from the condition probability, we can also be written like this: P of A given Bn equal to P of A intersection Bn divided by P of Bn. P of Bn. From that, I am taking this Bn to the left side. I am taking to the Bn to the left side. To take this Bn to the left side becomes P of A given Bn equal to. These both will be multiplied. So that is P of A given Bn into this Bn. And assume this as equation number 2. And if you substitute equation 2 in the above equation, this equation, then I will get what? So if you substitute here, see here, it is P of A intersection Bn, but here it is P of Bn intersection A. So both are same. Whatever may be, P of A intersection B and P of A B intersection A, both are always same. So that's why I can directly replace this Bn intersection A with P of A given Bn into P of Bn. So if you write like that, it can be like this. So P of Bn given A is equal to P of A intersection A given Bn into P of Bn divided by P of A. P of A. But we already know that from the total probability, P of A can be written like this: P of A equals sigma I equal 1 to n. P of A given Bn into P of Bn. So I will substitute this P of A in equation 3. Then what I will get? Then what I will get is like this: P of Bn given A equal to P of A given Bn into P of Bn divided by sigma I equal to 1 to n P of A given Bn into P of Bn. So this is called the Bayes theorem. So these two theorems are very important. So this total probability theorem and Bayes theorem, and you can expect these any one from in your external examination. So these are very important in the first unit. So the next we will see one problem. See this problem. A single card is drawn from a 52 card deck. Then what is the probability that the card is a jar? What is the probability that card will be 5 or smaller? And what is the probability that the card is a red 10? Red 10. Now see. So before doing the problem, we have to know so cards, around cards, about cards. So here what you know is in a card deck, in a deck there are 52 cards. In a deck there are 52 cards. Out of 52, 26 are black cards, 26 are black cards, and 26 are red cards. 26 are red cards. And these 26 black cards can be divided into. So in this 13 are one type of blacks and another was 13. So 13 there are 13 spades, 13 cards are spades and 13 cards are flowers. So somewhere in somewhere there are different names are there. And here these 26 cards can be divided into another way. So 13 diamond cards, 13 diamond cards and 13 hearts, 13 hearts. Now another one. These 52 cards. So in 13 spades you have numbers from 2 to 2 to 10, 2 to 10. So 2 to 10 means there are 9 cards and you have J K J Q K A. J Q K A. So that means that every 13 group of black cards contains what? These number of cards. That is, you have two number diamond, you have three number diamond up to 10 number diamond, and that you have J Q K A. That means in a card there are totally 36 numbered cards, numbered cards, and 16 letter cards. Letter cards. So number cards means what? These are numbered from 2 to 10, whereas 16 cards are letter cards means these are having J, Q, K, A. These are the letter cards. So this we should know while doing any problem. This we should know while doing any problem. Now moving on to our problem. Our problem, what they gave you is, so a single card is drawn from a 52 card deck. So what in the first problem? So if you take the first problem, what is the probability that the card is a jug? That the card is a jug. So how many jugs are there? Totally there are the jug cards are four jug cards are there. So four jug cards are there. That is one is from heart, one is from diamond, one is for spade, and one is for calabar. So totally there are four jack cards there. Out of four jack cards, we can get anything. So the probability of getting a jack card is 4 by 52. 4 by 52. That means the number of favorable cards are here 4, and the total number of cards are 52. So that's why the probability is 4 by 50. Now moving on to the second problem. Second problem. So what is the card? What is the probability that the card will be a 5 or smaller? So the card will be a 5 or smaller means the meaning is the card number should be 2, 3, 4, and so you can get any number of cards. But with this number there are totally 4 sets. 4 sets, that means you have totally 16 cards that are less than 5 number. Okay, so that's the 16 cards. So my probability P of getting 5 or smaller. P of getting 5 or smaller is number of favor cards are 16 and total number of cards are 50. Total number of cards are 52. So the probability is 16 by 52. That means 4 by 30. That is 4 by 13 and it is 1 by 13. If you make out the calculation, it becomes 1 by 13. Now, the third one is what is the probability that the card is a red 10? So red 10 means so C means the event is getting a red 10 card. So red 10 card means here there are totally 26 red cards. In 26 red cards, The 10 numbered cards are only 2. So 10 numbered, 10 numbered red cards. Red cards are only 2 only. So the probability is so favorable event is 2 and total number of events are 52. So the probability is 2 by 52 and is becomes 1 by 26. So before doing any problem, we should know this bar, this flow diagram, this flow diagram. So how many cards are there? How many black cards are there? How many red cards are there? In black cards, how many sets are there? 13, the two sets. One is of 13, another one is of 13. And in red cards, here also there are two sets, 13 diamonds, 13 hearts. So total 4 13s, it is equal to 52 cards. And again, these 13 cards can be divided like this. The numbered cards are from 2, 3, 4, 5, 6, 7, 8, 9, 10. And the letter cards are J, Q, K. So in a 13 set, there are 4 letter cards, 9 numbered cards. So finally, if you write together, you will get 36 numbered cards and 16 letter cards. 16 letter cards. You should know this one while doing problem. Suppose if they ask you in the same way in the cards problem, what is the probability of getting two queens? Two queens. So the problem is like this. What is the probability of getting two queens? Two queens. Two queens when when two cards are drawn. Two cards are drawn. So this is the problem. So two cards are drawn means you have to the probability is given as so the p equal to in the denominator it is like this. Two cards are drawn. So drawn means you have to write 52 C2. That means two cards are drawn from a deck of 52. 52 and here what I have to get two queen cards. So two queen cards means totally how many queen cards? Four queen cards. That means you can write 4C 4C2. So this is the probability. What is the probability of getting two queen cards when two cards are drawn from a deck? So similarly, if they gave you the same two cards are drawn, they want one is queen card, another one is a seven card, a seven card. So here one is queen card means it can be the denominator part is everywhere same. So here the denominator part is 52 C2 only. But in the numerator part, what you will get? You have to get one queen card. You have to get one seven card. So you have totally four queen cards. Out of four queen cards, you have to select one queen and into there are four seven cards. Out of four seven cards, you have to select one queen. So the probability is 4C1 into 4C1 divided by 52C2. So based on the given problem they gave you, the probabilities changes accordingly. So these cards problems are somewhat tricky. While doing these problems, you should carefully read the problem and do the solution. These are if you know the card about the cards very well, then it will be very easy. It will be very easy. So with this, I'll conclude today's topic. In the next class, we'll see about a random variable. What is meant by random variable? How to do operations on different random variables. So with this I'll conclude. So I request all of you to please subscribe Easy BTech channel. So we have uploaded number of subjects for BTech students. It will be very easy and you can get very good marks if you follow these videos. Thank you. Thank you very much.